Hi, we are Manuel Baradat and Jordi Saumell, and we will be briefly explaining some of the problems associated with transistor manufacturing and the recent advances that have been made to overcome them. This video will consist in two parts. The first part in which we will be explaining the problems and challenges that the industry has been facing during the last decades, and a second part in which will be explaining which have been the solutions that the industry has found to overcome them. These solutions consist in changing the approach in which the MOSFET transistors are designed and using new technologies as FinFET and FD-SOI. To begin with, the main challenge that the transistor industry has always needed to face is scaling. As you may know, Moore's law states that it is possible to reduce the size of the transistor by a half every 18 months, but this comes at a price of having associated problems, as we will see next. Apart from this scaling challenge, there's also worth noting that there's a trade-off between the scaling, the power consumption, and the final performance of the transistor. As we reduce the size of transistors, the gate may start losing the control over the channel, and there may be some current flowing while the transistor is in the off state. As we will later see, to overcome this, FinFET transistors were designed. Another undesired effect that becomes more relevant as we decrease the size of transistors are the leak currents. As we decrease the size of transistors, the gate oxide may become really thin, for example something about 5 atoms thick. Because of this, gate oxide may not behave as a perfect insulator and there may be some leakage. Similarly, decreasing the size of transistors causes that the junction leakage increases. Another effect is that when the transistor size is reduced, the fields in the channels are increased, as they are inversely proportional to L. This causes an increase in the velocity of the carriers, which reduces the carrier mobility.
As we have seen, an important issue when reducing the size of transistors is the leakage of current. The gate oxide that insulates between the gate and channel should be as thin as possible to increase channel conductivity when the transistor is on. But it is also necessary to reduce the leakage, or quantum tunneling, when it is off. So insulators of silicon dioxide typically have 4 or 5 atoms of thickness. Using materials with a higher dielectric constant allows increasing the thickness while maintaining a high capacitance, and a thicker insulator means less leakage. In the table, we can see typical materials that are used to increase the dielectric constants. Another consequence of scaling transistors down is that the fields in the channel and the dopant's impurity levels increase, which reduces the carrier mobility. To increase carrier mobility, we can introduce mechanical strain in the channel, either to increase the mobility of electrons, holes, or both of them. This strain can be in one axis or in both, and is achieved typically with germanium. Germanium has a larger atomic radius than silicon, so replacing some atoms keeps the shape but leaves mechanical strain. In the figure, you can see on the left an NMOS transistor strained, and on the right a PMOS transistor also strained. Finally, the switching delay of transistors is typically considered to be caused by the capacitance of the transistor gates. However, when transistors become very small, the capacitances between interconnections become greater. As wires get nearer, this capacitance also affects the delay of the transistor. To correct this problem, we need materials with lower dielectric constants, so that capacitances are lower. As you can see in the table, adding carbon to the silicon dioxide reduces the dielectric constant. The same happens when adding porous to the material. Finally, on the image on the left, we can see the use of air, which has the lowest dielectric constant.
FinFET transistors were designed to overcome the inability of the gate to turn off the channel when the size of transistors, and particularly the size of the gate, was reduced. We will see the main characteristics of this type of transistors in the following 3D representation. This is the structure of the classical bulk CMOS transistor, with the source, the drain, the gate, and the other common elements we usually find. The gate has a length and a width. We also know that the current should only flow when the transistor is in the on state. When we reduce L, the transistor may also conduct in the off state, and this is a problem. To overcome this, the FinFET structure was designed. The FinFET structure consists on having the gate electrode around the channel instead of having it only on the top of the channel. A thin film of silicon accesses the channel and it is surrounded by the gate electrode. The source and drain are those regions not covered by the gate. The source and the drain regions consist on the silicon fin and extension implant surrounded by a polyoxide. Internally, the region between the source and the drain is surrounded by a dielectric and a metal. Now, when the transistor is in the on state, the gate has excellent control over the channel because it is much more exposed. We can control this exposition using more parameters than in classical MOS. As in classical MOS, when the gate electrode is energized, it forms a pathway between the drain and the source for which the current can flow. To enhance performance, silicon germanium or silicon carbon stressors are laid over the source and the drain, as it is also done in common CMOS transistors. Finally, for manufacturing reasons, the electron gate is uniform across the transistor. This is the final design for FinFET transistors, which is also known as tree-gate. So to wrap up, remember, MOSFET on top and FinFET around.
When scaling down, leakage current becomes a significant proportion of power consumption. FDSOI, which stands for fully depleted silicon on insulator, is a planar process that allows reduced silicon geometries while simplifying the manufacturing process. As you can see in the figure in the right, a ultra-thin layer of insulator, barium oxide, is placed on top of the base silicon. A very thin silicon film implements the transistor channel. This channel doesn't need doping because of its thinness. As you can see in the image on the left, the barium oxide lowers the parasitic capacitance, which is represented with arrows, between source and drain. This way, electrons flowing from source to drain are confined, which significantly reduces the leakage. FDSOI allows polarizing the substrate underneath the device to control the behavior of the transistor. It is similar to body biasing from bulk technology, but body biasing has a lot of current leakage at reduced sizes, whereas FDSOI doesn't. Finally, with forward body biasing, the transistor can be switched faster. This can be modulated dynamically during operation, which allows making faster circuits or power-efficient circuits according to what is necessary. Finally, the simplicity of the manufacturing process makes FDSOI devices more economical. Also, this design allows faster operation at low voltages and a better management of the energy. In the figure, you can see the speed in the abscissa and the energy efficiency in the coordinate. The green and red lines are bulk technologies, and the blue lines represent FDSOI. Given a speed, FDSOI is clearly more efficient.